Alright, so we want to find the value of the derivative at the function's extremum or at an extremum, or a place where it's changing direction. So this function changes direction right here. It has a minimum right here at -2, 0. So we want to know what would the derivative equal. This goes to a sharp point. You can't take the derivative of a sharp point, so f prime of 2 would be undefined, or it doesn't exist.
I mean, you should check, or if it looks like that, it's just...
Right, well there's only two options when it's a maximum or minimum. Either the first derivative is 0, or it's undefined. If let's say this thing kept going over here like this, and maybe over here it came up and it turned around, and this was the point 1, 2. Then the first derivative at 1, I know is 0.
But I mean, I'm just saying, like, you're okay to eyeball something like that and say...
Oh yeah, because notice too how this it's concave down and concave down.
Yeah.
You can't have a smooth turnaround if you're always concave down. It's got to, it's got to curve the way it's going. You can't curve the opposite. Oh, negative 2. Yeah, so at -2, the derivative is undefined. We have a minimum. At 1, it's 0. We have a maximum. So if it's a smooth curve, the derivative is 0. If it's a point, it's undefined.
So you have it's 2 sides.
Let's see. So a rancher is 500 feet with which to enclose 2 adjacent rectangular corrals. So you're right. There's going to be 2 corrals, and they're right next to each other. So something like that. What dimensions should be used so the area would be a maximum? So let's maybe call this x, and all the way across here y.
You just have 3 times for your...
Well, yeah, but what would the area of that be? X, y, right? That's what we want. We want the area to be a maximum. So this is x, that's y, there's the area. We need the area in one variable. So here's where we use the fact that it has 500 feet of fencing. That's x, that's x, that's x. This all the way across here is y. So that tells me 3x plus 2y is 500. I can solve this for y in terms of x and plug it in.
That's great.
But it's not ludicrous. So 2y would be 500 minus 3x. All right, then divide both sides by 2, and y would be 250, or 250, minus 3/2 x. So now I come over here to the area, and I can write the area in terms of x. Because we want to maximize the area.
Oh,
500 is how much fencing he has.
Oh, that's right.
So the area in terms of x would be x times y, which now we know is 250 minus 3/2 x.
Isn't the amount of... I mean, it seems to me like the amount of fencing is almost arbitrary because like, you don't always end up using all of that.
Oh yeah, we're going to use solid.
Yeah, of course.
So we distribute that. Now maximums and minimums occur where the first derivative is 0 or undefined. So we take the first derivative and we get 250 minus 3x. So that's never undefined, so we figure out where it's 0. So we take 250 minus 3x and set it equal to 0. So we need to know where does 3x equal 250. So x is 250 over 3. What does that sound like, 83 to the third? And let's see, it was feet.
So that's your x and you have to put it back in which you are.
Yeah. And let's see, what were they asked? What did I ask for in this instance? Yeah, what dimension? So if that's our x, we come right here to find the y. Right, so the y would be 250 minus 3/2. Probably be easier to leave the x is 250 over 3. Right, that way the 3's will cancel. Okay, 250 divided by 2 is 125. So the y would be 125. So So y is 125 feet, and the x is 83 or 30.
If this was like different, let's say if we were just trying to find like a rectangle on its own side, and it was like, let's say 85, how would we go then?
So you're saying maybe if there's a river flowing like this, and somebody wanted to make a rectangular corral, this, how many feet of fencing do they have?
85.
Who remembers this from the take home? Terry's trying to. Where is it?
I told you.
Oh, it's 24 minutes. This one?
No, I think it was on the
You don't look at the homework.
whatever, it was on the homework, it was like,
No, let me finish this one. Well, Terry, let's say a farmer wants to build a corral with the river as one side, he's got 2,400 feet of fencing. Let's call this side of the corral X, we'll call this side Y.
and so the area would be like X times Y.
Area is X times Y. What would 2X plus Y equal? That equal 2,400, right? So you have 2,400 feet of fencing, so subtract 2X from both sides, Y would be 2,400 minus 2X. So we can put that in here for Y, and now the area, in terms of X, would be X times 2,400 minus 2X.
This isn't one like, or like the last one where you could put, like it into your calculator and do the tracing the max or the min, right?
You could.
But you, because then you get your x value and you still put it back into the one. Yeah.
So like this, so we get this, so if we take the first derivative,
Yeah, I think on
Or you wouldn't find the max, right? Then you would find the intercept, right?
this one allowed us to do the graphic calculator.
so we get 2,400 minus 4X. So we'd set that equal to 0. So we want 4X to equal 2,400. So X would be 600 feet. So if X is 600, Y is 2,400 minus 2 times X. Y would be 1,200. Because if he was saying the problem said the farmer had 2,500 feet of fencing, so like, that was part of the problem, said the farmer had that many feet of fence. Yeah, like a farmer has 2,400 feet of fencing to make a corral.
And it's close.
So that was given in the problem. So he's going to put the corral here and here, he doesn't need a side there, so this plus this equals how much fencing he needs. So what do you got?
What's the equation that you put in the calculator?
This one?
So you use 4x.
Well, I would even do it here, I would do X times 2,400 minus 2X. All right, and if you think about the window, X could go from 0, I'll say to 1,200. And then hit zoom fit. Okay.
And we're trying to find when y is 0, right?
No, we want the maximum. In this case,
But
Y
no,
would
we're
be,
setting it equal to 0.
we set the first derivative. This is the original function. So I graph that, there's my maximum right there. So second, calc, maximum. Figure it out from 0 to 1,200.
So you're still doing the same thing, which is trying to find the maximum.
Right.
Which in this case just gives you your x value and such.
Tells me the X is 6,000, but look at the Y is 720,000. What do you get if you multiply 600 by 12? 720,000. Right, so it's telling you the X and the maximum area. It doesn't tell you the Y. In this case, the Y is the area. So the f be the function given by f of x is 2x cubed plus 9x minus 12. Find all the numbers and satisfy the conclusion of the mean value theorem on the interval -1. Megan, what this is saying, we want to find all the numbers where the instantaneous rate of change equals the average rate of change. So how do you find the instantaneous rate of change? First derivative, right? Slope of a tangent line, the velocity, instantaneous rate of change. So basically, we want to take the first derivative and set it to the average rate of change. The average rate of change would be f of b minus f of a over b minus a. Entropy would tell you that's just the slope of the line. The second line minus the first line, the second x minus the first line. So the first derivative here would be 6x squared plus 9. And then that would equal, to the derivative of that, that's going to equal f of 3 minus f of -1 over 3 minus negative. So we get 6x squared plus 9 equals, if I plug 3 in the original equation, so 27, I get 54, plus 27 is 81, minus 12 is 69. Minus, plug in -1, I'll get -2, minus 9 is -11, minus 12 is -23. That's over 3 plus 1 would be 4. So we get 6x squared plus 9. And here, this is going to be 92 over 4 is 23. With me, Andy? So subtract 9 from both sides, and 6x squared would equal 14. Divide by 6, x squared would be 7/3. Take the square root of both sides. X is plus or minus the square root of 7 over the square root of 3. Which if we rationalize that by multiplying by square root of 3, top, bottom, we get the square root of 21 over 3. But we can only look for numbers in between -1 and 3. So square root of 21, that's bigger than 4, right? The square root of 16 is 4. So this would be like -4 over 3. That's smaller than -1. So we don't use the negative. We just take the positive square root of 21. I know this was without calculator, but what that's really doing here is if we graph this function, if I come into the y equals here and I put 2x cubed plus 9x minus 12. And let's see, I'll take the window and I'll go from -1 to 3. We're going to hit zoom fit. There's the graph. So let's just take a picture of this. And when I look at this graph, what we did here is if we put a point right here at -1 and a point over here when x is 3, and we draw a tangent or a secant line, or a line that connects those 2 points. We figured out there's only one tangent line, so about right here somewhere, that's parallel to that one. And we figured out that the point where this is parallel is at the square root of 21 over 3. That's what we figured out.
Secant line, I think I have a graph that our function eliminates all kinds of curvy lines all over the place.
All kinds of curvy line laws.
So we have something like that. And then it tells us to do it from a certain point, like let's say where x is 0.
Okay.
And then let's do that next new point, though, right?
Right here.
between there, and let's draw a secant line and find all the points parallel. So does this?
You can only do it the
or all-
ones
yeah,
in
sorry.
between there.
Yeah,
So it
So-
seems like there's only probably one, maybe
Yeah.
about here
So
somewhere.
maybe the interval's too small, so bump the interval back to like,
But that,
so, okay, well, this is probably not, I'm not gonna make an interval. But
All right,
whatever,
well,
what if the tangent line crosses multiple places?
so what if we change this? What if we took this and maybe we said this one from here, we went all the way over to here?
I had the same issue.
Yeah.
Okay, so we draw a secant line here.
So you have a secant line, which I have an issue with anyways, because it passes through. It's not just those two points. But that doesn't
Right,
matter,
but
right?
it's,
We just care about the secant line if it connects.
yeah, we're just saying it connects those 2 points. So that's really the average rate of change. Another one here somewhere,
Even though it's, wait, but
another
but
one
it becomes
here.
secant because it would go through.
that's gonna cross at some
But-
point, right?
True, but at that point, it's tangent.
The non, that.
What's in the?
Just at that point, see here, at this point right here,
Yeah,
at this point right here, at this point right here, and this point right here,
It's not crossing.
those lines are tangent. You're right, this one here, if I took this and I extended it out,
yeah.
yeah, it crosses it again. But it's tangent at this
It's
point.
tangent at that point and parallel to the secant line, so that would be a solution if that's
Solution.
the question.
Yeah,
We
so,
have several points that would satisfy.
oh yeah, you can have plethora. So almost think of these like those slow faces, mini tangent. Hey, settle down. We have 1, 2, 3, 4, 5. I would think one here, another one here somewhere, 2, 3, and maybe up there another one. But it's for,
just had that when we had that.
yeah, concavity changes.
That's it, no more?
Those are the only inflection points, yeah.
So we have only 1, 2, 3 here?
Probably about 3.
You don't have to start at the beginning and there.
No. But that, just looking at a graph, it's hard to find the inflection points. You'd actually need the function, find the second derivative. Yeah.
So we get 3 values in the second value, that we have
3 possible ones. Then you want to set up like those intervals and check, does it change from concave up to concave down and vice versa? So instead of, guys, let's do this. Let's remember the intervals in which the graph of this, instead of saying, well, let's find where it's concave up and find points of inflection. So we'll add that up. We'll find all points of inflection. So an inflection point is where a graph changes concavity. Or in other words, where the second derivative changes sign. So to find concave up, concave down points of inflection, we need the second derivative. So the first derivative here, e raised to a power, the derivative is e raised to the power times the derivative of the power. So derivative of negative x squared would be negative 2x over 2, or negative x. So there's the first derivative. Second derivative would be the product rule. So the derivative of e to the negative x squared over 2 is e to the negative x squared over 2 times negative x. Right? But then we got to multiply that by negative x. Right, because this is just the derivative of this. So we got to multiply by that. Then plus the derivative of negative x, which is negative 1, times e to the negative x squared over 2. So now, no, because I did, here's this right here is the derivative of this, right? So I took the derivative of this, got this, multiplied by that. Then I took the derivative of this, which was this, and multiplied it by this. So now, if I look at this, to find points of concavity, we need to know where the second derivative is 0. So I'm going to factor an e to the negative x squared over 2 out of both of these terms. And then here I'll be left with negative x times negative x, which is x squared. And over here I'm left with negative 1. Right, so all I've done there is I factored this out of both terms. I take it out of here, I'm left with this times this, which is x squared. Take it out of here, I'm left with minus 1. Now, this can never be 0, right?
So it has to be there.
So this factors to x minus 1 times x plus 1. So our x's are plus or minus 1. All right, if I leave this here for a minute, x squared over 2. All right, now if these are possible points of inflection, then what we have to do is set up intervals. Go from negative infinity to the smaller one. All right, then the smaller one to the bigger one. Then from the bigger one to infinity. And check what it does to the second derivative. So some number less than negative 1, say I pick negative 2. E raised to a power is always positive, so I don't worry about that. Negative 2 minus 1 is negative. Negative 2 plus 1 is negative. Negative times a negative makes a positive. In between negative 1 and 1, I can pick 0. That's positive. 0 minus 1 is negative. 0 plus 1 is positive. Negative times a positive makes a negative. Bigger than 1, everything is positive, so we get a positive. So the question said here, where is it concave up? It's concave up from negative infinity to negative 1, and then again from 1 to infinity. Right? If we would have asked where's it concave down, we could say it's concave down. Yeah, from negative 1 to 1. But then to find points of inflection, okay, points of inflection, since at negative 1 it went from concave up to concave down, there's a point of inflection when x is negative 1. Then at 1 it went from concave down to concave up, so there's a point of inflection when x is 1. We got to go back to the original function to find the y's. So I need to find f of negative 1. So that would be e to the negative 1 squared is 1. That makes it negative 1 over 2. E to the negative 1 half. Which we can make 1 over e to the half, or even make it nicer, I guess, make it 1 over square root of e. I don't know if that's any nicer. Leave it like that, right like that, I don't care. So one of the points of inflection, when x is negative 1, the y is e to the negative half. Right? If I put positive 1 in here, would it be any different? It would be the same thing. So there's also 1 at 1, e to the negative 1. So there's our points of inflection. Here's where it's concave up.
If there's any like e to the x of anything in there, you can't set it to 0? Is that what you're saying?
No.
Oh, okay.
Anything raised to a power can never be 0, right?
Right, okay.
So e raised to a power.
So you just forget about it here when you're setting.
When I'm trying to figure out where it equals 0.
Right. Okay, good. Because sometimes they forget algebra. So
Well, yeah, what if we did do that, if I took e to the negative x squared over 2, set it equal to 0, first thing I would want to do is take the natural log of both sides to get the exponent in front. Right? Then I get negative x squared over 2 times the natural log of e. But then we run into the problem. What's the natural log of 0? Can't do it.
okay.
So e raised to the power of 0 is 0. Those are part hard to see on the graph.
I mean, like, we have to get result for the original function of the second derivative.
Second derivative. But now I'm glad you asked this because we can actually get them from the first derivative too. Just watch here. If we put the original function in, if I put e raised to the negative x squared divided by 2. I just go back to zoom 6, a standard graph. On the regular graph, it's hard to see. We can sort of see something there. If I go zoom box, and just box this in. All right, so get there, hit enter to anchor it, and then just put a box around what I want to look at. It looks like there's a point of inflection right there. It goes from concave up to concave down. Then again, about right here, concave down, concave up. I could go second, calc. You know, we figured out it was 1. You know, do value and put in 1.
Or you could eyeball it.
No. Well, this one maybe. But if we put the first derivative in, right? We found the first derivative without too much trouble. Right, the first derivative was e to the negative x squared over 2 times negative x. If I graph that, an interesting thing happens to that graph. Where does it have a maximum? Second calc, I'll do maximum. And I'll move the cursor to the left. Just get past that highest point, hit enter, and move to the right. Hit enter, and enter again. So when x is negative 0.999, it's really negative 1. I don't know why the calculator does that. But it's interesting where a function where the first derivative changes direction, the second derivative is 0. Right? Because the derivative, when the derivative is 0, the second derivative is the derivative of this. When the second derivative is 0, the derivative should be changing direction. When the first derivative is going up, it tells us the second derivative is positive. Right? If the second derivative is the derivative, when the second derivative's first derivative is going up, the second derivative is positive. See, and that bears with it here. It goes up until we get to 1, or negative 1. Then it goes down until we get to 1. The second derivative is negative. Because the second derivative is the derivative of the derivative. When the derivative of something is negative, that thing's going down. So when the second derivative is negative, the first derivative is going down. When the second derivative is positive, the first derivative is going up. So maximums and minimums of the first derivative are points of inflection of the second derivative. This is a good one. Rectangular page, and this is with calculator. The rectangular page is contain 30 square inches of print. The margins on each side are 1 inch. Find the dimensions of the page such that the least amount of paper is used. They're what? Are they? I don't know. Did I leave them up there? Terry, would you say there's a plethora? All right, so it's a pretty good rectangle. There's a rectangular piece of paper. Okay, it has to contain 30 square inches of print, and there's going to be margins. So inside here, this is going to be 30 square inches. The area here is 30 square inches. And we want a 1 inch margin on each side. So there's an inch here. From there to there, inch here. Same thing over here, and same thing down here. So we want to find the dimensions of the page so the least amount of paper is used. So we want to label this somehow. And I would probably suggest calling this X and this Y. For the main reason is when they tell us this printable region has to be 30, now we know what X times Y is. Right, x times y is 30. That gives us a place to start. X times y is 30. Now, we want the dimensions of the page. Well, this page, this is y, and then plus 1, plus 1. So that's y plus 2. And I'm going to think here the area of the entire page. That's y plus 2. What's this? X plus 2. So now, if I multiply this out to get the area, I can either multiply it out now, or I can do some substituting. Multiply it out first. Okay, if I multiply this out, I'll get x times y plus 2y plus 2x plus 4. If I pull that out. And then over here, if x times y is 30, that tells me y is 30 over x. I can replace this y with 30 over x. Yep, replace the xy with 30. So the area is going to be 30 plus 2 times y, which is 30 over x, plus 2x plus 4. So the area here, see, this would be 60 over x plus 2x. So I'll say 2x plus 60 over x plus 34. Terry, weren't you the one that said maximums and minimums occur with the first derivative is 0 or undefined? So if we take the first derivative, we get 2 plus, we can think of this as 60x to the negative 1. So actually the derivative of that would be negative 60x to the negative 2. So we want to know where that equals 0 or where it's undefined. Well, this is really 60 over x squared. So it's undefined when x is 0. What do you think 0 for x gives us? If this is 0, then we have nothing, right? It's a minimum. So then if we take this over here, we'll get 2 equals 60 over x squared. Cross multiply 2x squared is 60. Divide by 2, x squared is 30. So x is plus or minus square root of 30. Hopefully it's not minus 30. Right, square root of 30. You can't have negative, so it's square root of 30. So if we estimate that, this is with calculator. The square root of 30 is about 5.477. Okay, so they're asking for the dimensions of the page. So if this is 5.477, the page has another inch this way, another inch this way. The width of the paper is 7.54. 7.477. And then what we got to do is find the y, right? So if y was 30 over x, y is going to be 30 over that 5.477, which I got a feeling is going to be close to 5.477. So we add an inch to each side, and we get 7.477. They were inches, so we'll mark for inches. Okay, now, since this was on the width calculator part of the test, I could have, at this point right here, graphed the area function. Right, the area was 30 plus 2 times 30 over x plus 2x plus 4. Maybe think if it's 30 square inches, I can't see the x being bigger than
Maybe I will set 10 to start out. I'll do 10 and do zoom fit. Came down, I never saw it going back up. Huh? So maybe I'll change the window, maybe go to 25, but now I'm starting to think maybe I made it zoom fit. The X is too big. Oh, now I can see it coming back. So all I gotta do is find this minimum, so I'll do second calc minimum. And let's have a check in between 0 and 25. What's the lowest this graph is? That's when X is 5.477. So with calculator, you can get it from this point right here by graphing the line of minimum. Without a calculator, you gotta take the first root